Hi, and welcome to Module 5 of Lecture 15. In the next module, we're going to introduce and do some examples for the last of the types of multivariable optimization we're going to deal with in this course, and that is constrained optimization using inequality constraints. Now, sadly, because it's just the most complicated of the three, this is also the one that's most commonly seen in practical social science problems. The reason is straightforward. We've talked about it before. Oftentimes, whereas in something like physics, you're constrained to, say, walk on the surface of the Earth without some kind of mechanical aid, in practice, in social problems, you're often not constrained to exactly satisfy some constraint. So one thing we talked about was a budget constraint. We previously said that if you had a budget constraint but non-satiable preferences, then you would want more and more of something and therefore always spend your entire budget, and therefore the budget constraint would actually bind in the sense that you'd be forced to spend exactly your total budget and not any more than that because you'd want to spend more than that, but the constraint binds you to spending only that much. So in that case, we could convert it into an equality constraint. However, if you had, for instance, satiable preferences, you had enough of something, right? You had eaten your fill of apples and oranges from the previous example and decided, you know what, I'm done with apples and oranges. I don't want any more. In that case, you would not want to spend your entire budget. You can see an example of that pretty easily with the apples and orange example, right? If you had something like a policy, or apples and oranges in this case, right? So here's the number of apples you actually had, minus your ideal apple total. And then here's your number of oranges you actually had, minus your ideal orange total. Well, as we saw in the unconstrained optimization problem, you would want that many apples only, and that many oranges only. That's your optimum. Well, if your budget were such that you could actually afford those things, so if, and this is the number of apples now, if this were actually less than your budget constraint, then you would buy all the apples and oranges you wanted, and your budget constraint would not bind. You would not buy all the rest of the apples and oranges possible, and this budget constraint would not bind. It would be what we call slack. So this would be a slack constraint. If, in contrast, the ideal number of apples or oranges were greater than b, I should say, then you would have a situation in which they would bind. The constraint would bind because you'd be forced by the constraint to have this condition here. And there's also the knife edge condition where this is true by itself. It just happen to be the case that you exactly the right number of apples and oranges. That's a little rarer. Exactly the right budget, rather. But the two sort of categories are either the constraint binds you, sort of forces you to not exceed, in this case, the budget constraint when you would want to, or it does not bind you and it's slack, in which case the constraint does nothing. It has absolutely no effect on you. The fact that you have $1 billion to spend on apples and oranges doesn't matter if you only want 2 apples and 3 oranges, right? The constraint's irrelevant. The budget constraint need not be considered. So this is one example of when you use these things. The far more common example in political science, and I think most social sciences, is non-negativity constraints. It's non-negativity constraints. And these take the form of this. All right, we discussed this before as well. Oftentimes you can't spend negative money, right? You can't take back campaign contributions from a candidate, right? You can't mobilize negative troops for war, right? So oftentimes we want to constrain our variable to be greater than or equal to 0. Now sometimes that constraint will be slack. That's slack whenever the optimum x ignoring the constraint would be greater than 0. You don't need to force it to be non-negative if you want to have a positive number there, right? So that would be a slack constraint, and we don't want to actually include that in our constraints because it's just going to take up room, right? It has no effect. Whereas, and I'll put the less than here, it's the knife edge case of equal comes up not as frequently. If you would want less than or equal to 0, however, then the constraint binds. Technically speaking, if you would want exactly 0, the constraint doesn't bind, but it's a knife edge case, so we're just going to stick it with the binding case. In this case, the existence of the constraint, the existence of a non-negativity constraint, forces you to have 0 instead of the negative number you might have otherwise wanted. So in that case, the constraint binds, and we want to include it. So this is when we use these things. Now, what we're going to do to make use of this is basically take a variant of the Lagrange setup. Okay. And this whole setup is named after Kuhn-Tucker. There are sort of three things. There's an H over here. There are Kuhn-Tucker multipliers. There are Kuhn-Tucker conditions. And there's a Kuhn-Tucker theorem. We'll deal with them in this order. Okay. So the first thing we're going to do is set up a Lagrange type function here. So we're going to do that by setting up the original one. And let me back up a step. The problem here is this. The general problem. You have maximize, and here I'm going to stick with maximization for the moment. Maximize some function f subject to two kinds of conditions. One, a bunch of equality constraints of the exact same type you saw in the previous two modules. And two, a bunch of inequality constraints that are new. These inequality constraints should always be phrased as some constraint is less than or equal to some constant d. So h is a function here, g is a function, excuse me, which I would have written as functions on this tab, but except I have limited room, I don't want to take up all the space. But f and g and h are functions. Okay, so what we're going to do here is write this thing in terms of a Lagrange type function. So first we're going to stick in the f, and this will be a function of all our variables as usual. Now we're going to stick in all our equality conditions. Right? And this is going to be the same as usual. But now, we're again going to convert this to the format such that this thing equals 0. Right? We're going to convert this to the format that g equals 0 with the exact same logic as before. Because the equality constraints will bind in equilibrium, we want to force the constraints to appear in the system of equations we will get when we differentiate. By doing this, we will force that to happen. Same as before, there's no new logic. It's identical to the previous case. And we can safely add this to our Lagrange type function because, again, it's 0 in equilibrium. We're adding nothing. We're just forcing the constraints to bind, the equality constraints. Okay. So that's what's done before. Now we're adding here, to add the Kuhn-Tucker conditions here, we're going to add some multipliers for the inequality constraints. And that's a mu sub j, hj, which is a function of the x's, and also this d. And this d has to be less than or equal to 0. Sorry, this h. This h has to be less than or equal to 0. So again, we're going to convert this condition up here. I'm going to make that actually in red. We're going to convert this condition here by subtracting di from the left side to this thing down here, and this thing down here, I should probably include that, has to be less than or equal to 0. So same as before, we converted g into some constraint that said g equals 0. Now we're going to convert the h into some form that says h is less than or equal to 0. The less than or equal to 0 is important. Always make sure the h is less than or equal to 0 to get the signs right. This is for a maximization problem, and this gives you, and these things here, these mu's are Kuhn-Tucker multipliers. In general, we care less about them than we care about Lagrange multipliers. So in this case, because it's going to be more complicated in some other ways, we're going to stop caring about certain things. So, to wit, we're going to drop the c and the d because we don't care about them at all here. I'm also not going to interpret the lambdas and the mu's in this case because whatever. We're going to focus on the actual core problem of maximization. I should also say that if we were to minimize, which I'll write in blue, then this would be a positive. Otherwise, it's the exact same problem. We just switched the negative to a positive in front of the mu. That's for a minimization problem. But typically, we maximize functions that are constrained because utility is the most common thing we maximize. Okay, so this is the setup here, the Lagrange type function with Kuhn-Tucker multipliers mu here. So that's the first thing. Now, a couple notes about Kuhn-Tucker multipliers. Now, lambdas you end up solving for, and that's fine, they stay the same. Everything's the same with the lambdas before. But what about this term here? This last term. I should wait to wait. What about this last term here? Well, keep in mind part of our logic for subtracting these lambda g's was that in equilibrium, right? When you solve the whole system, that term is 0. What about this last term, the mu h? Well, if the h binds, if the constraint binds, so if you're forced to, for instance, spend your entire budget, and you had a budget constraint, that looks like, if that d was a b up here, and you had a budget constraint, right? And your h was less than equal to budget constraint. If that constraint bound, right? So if you spent all your money and the budget constraint bounded you to spend that money, then that thing would also be 0. H would be 0, right? It would be exactly equal to 0 because the constraint binds. So it would be no different than an inequality constraint in equilibrium because the constraint would bind in equilibrium, and that term would be 0. So that would be no problem at all. So that's one possibility. One possibility is that the constraint, I'm already going to drop the d. So that's one possibility, the constraint binds. If that's true, then the mu j's will be non-negative. Again, we're not going to discuss why in this case, but the important thing is as long as you keep the sign correct, as long as you negative sign out front, and make sure your h's are less than or equal to 0, then the mu's will be non-negative. Okay. So, and I said before, we're not going to go through all the intuition of every step, every piece of these techniques now at this point in the course, but that as long as you keep the signs correctly, that'll be greater than or equal to 0. Okay. That's one possibility. But the other possibility is the constraint does not bind. It's slack. So the fact that the constraint exists is there, it doesn't affect anything in equilibrium because you wouldn't ever, for instance, use your whole budget. Or you would choose a positive number. In that case, if the constraint if the constraint is slack, so it does not bind, we have to get rid of that term, right? Because otherwise we're subtracting this term that's not 0 in equilibrium from our function, and we're going to mess up our overall maximization. And this is, again, loosely speaking. I'm trying to give you intuition for this. This is very loosely speaking, as most of the book is. So loosely speaking, we're going to basically subtracting a term that's not 0 in equilibrium, and that's not good, right? We're going to mess up our whole maximization problem. So we're going to have to set, this is a mu, sorry, it looks like an m. But we're going to set mu equal to 0 for those cases. So if the constraint is slack, then we're going to set mu equal to 0 to force that term to go away. Right? If mu is 0, the whole term vanishes, and we've still subtracted 0. So these two sort of conditions combined do is force that last term to be 0 in equilibrium always. Because two of them, they are called complementary slackness conditions. Oops, I'll put the dot over the O. Okay, complementary slackness conditions. Okay, so that's most of the setup, right? So basically, that's the added wrinkle here. The Kuhn-Tucker conditions consist of a set of conditions derived in the following fashion. First, you differentiate your Lagrange type function here with respect to all the x's, all the components of x, and also all the lambdas. That's exactly as you did for equality constraints, and you'll get the exact same system of equations from those differentiations. Nothing's changed there. What's added are the new conditions, the complementary slackness conditions. Because you can't differentiate with respect to the mu's, because sometimes they're just identically 0, and the h's are not actually binding, instead of differentiating with respect to mu's and adding those to the system of equations you get from differentiating with respect to the x's and the lambdas, you are instead going to list all the complementary slackness conditions, and there's a nice way of writing those together, which is for every inequality constraint you have, you must set that equal to 0. That guarantees that either h is 0 or mu is 0. So for every single constraint you have, you're going to add this one. So again, you're going to, we'll go through the whole series of steps at the end of this module, but again, what you're going to do is first differentiate your Lagrange type function there with respect to the x's and the lambdas as before. You get a system of equations. To those equations you add one of these conditions down here, which I'll again write in red, for every inequality constraint you have. The most typical one you'll have is the non-negativity constraint. Note that since your non-negativity constraint looks like this naturally, x is greater than or equal to 0, you must convert that to negative x is less than or equal to 0 when you include it in your equation. So non-negativity constraints will often look like this. So say the one for x, for instance, would look like this. Sorry, would look like this. That's an equals. Instead of the other way. Important to note though is when you stick it in the Lagrangian and then the Lagrange type function, since there's a negative x out front here, that's going to flip this negative sign out front. So you're going to end up with, for those kinds of conditions, you're going to end up with a positive mu x in the Lagrange type function. So when you differentiate with respect to x, you're going to get the mu x's there. Which brings me to my last sort of difference here. The mu's enter in two ways. One, through the complementary slackness conditions here. So there'll be a set of slackness conditions at the end of your other conditions that altogether comprise the Kuhn-Tucker conditions. And each condition will be associated with one inequality constraint, and it'll just be mu times h equal to 0. So that makes either mu equal to 0 or h equal to 0. Mu's will also enter, just like lambdas did, when you differentiate your original function, your Lagrange type function, with respect to the x's. Because the mu's, right, are multiplying the h's, which are functions of x's, in some cases just simple functions, x, right, for this case over here. So when you differentiate with respect to x, you end up with a mu. So they will appear elsewhere in your system of equations. And we'll see this in the examples in the next module. So just like lambdas appear both in the equation, the condition that ends up just replicating your constraint, lambdas also appear in the conditions related to your first order conditions of f. Similarly, mu's will appear in your complementary slackness conditions and also in your equations representing the first order conditions for f. So you have to solve this whole system of equations. Okay. So that's almost everything here. There's one more thing to talk about. And that is, how do you know if mu is 0 or h is 0? Right? This equation right here, the slackness conditions, will never tell you that. Right? So you can't just use these sort of in the equations in the system itself, because you will never learn from that system if mu is 0 or h is 0. So, and here's where these things get unpleasant. What you have to do is consider every possible case. So you'll go through and do the entire problem assuming mu equals 0 and h is not 0. And then you would do the entire problem again assuming h is 0 and mu is any non-negative number. So I said again. First you would split this whole problem into two cases for the first single non-negativity constraint. One case would have h equal to 0 and mu be any non-negative number, and the other case would have mu equal to 0 and h be strictly less than 0. And you have to do each one separately. So the reason this is messy is if you had, say, two variables and another constraint, like a budget constraint, that may not bind, you would have 2 times 2 times 2, or 8 cases. Right? You can very rapidly get into a large number of cases using in this approach, and that can get to be a pain in the neck. Now, it'll turn out when you do this, a lot of these cases will end up not being consistent and have no solution, and you won't have any solution to the maximization problem with those cases. So that's so that'll get rid of a lot of the possible cases. You won't have necessarily 8 possible things to compare, one for each case, but you might still have 2 or 3, and you still have to go through all 8 cases to find the ones that actually are consistent and do have a solution, a possible maximization, a possible maximum. So this is where it gets a little messy, and we'll see how to do this in practice. We'll go over this again briefly at the end of this module in a few moments, when we list a whole series of steps, and we'll also see how this works in practice and examples at the end and the last module in this lecture. And of all the sort of example modules, it's probably most important that you really work through those examples in the example module, because getting a hang of how these cases work is difficult at first, but it turns out that it's not so bad. It's mostly bookkeeping. You just do the same thing over and over again. You're basically effectively doing the equality constraints several times instead of just once. So you're solving the system of equations over and over again. So we'll do a couple of examples there, one easier, one harder. Okay, so that's almost everything for the setup. I did not mention yet the Kuhn-Tucker theorem, right? So the Kuhn-Tucker multipliers were all these lambdas and mu's. The Kuhn-Tucker conditions were the set of equations you get when including the differentiation of the Lagrange type function with respect to lambda and the x's, and then adding the complementary slackness conditions. I did not mention the theorem. I also did not mention how to ensure this is a maximum. Well, you could in theory go through and compute border Hessians for all different cases. So in some cases the constraints would bind and you'd have borders. In some cases they would not bind, you would have no borders. In some cases some of them would bind. There'd be a lot of different things to deal with. In practice, it's a lot easier to make certain strong assumptions on the nature of the problem itself and use the Kuhn-Tucker theorem to say it's a maximum. So it turns out if f is concave, so if your objective function f that you're maximizing is concave, and your constraints are quasi-convex, or convex which is stronger, then the Kuhn-Tucker conditions will produce a maximum. And I'll write it up again. I just want to leave this up for a second. Actually, you know what? I'm going to get rid of this and write it up again. Okay. So the Kuhn-Tucker theorem. If f is concave, and all the gi and hi are quasi-convex, or convex, which is stronger, then you have a maximum. So you don't have to bother. So if these are all true, you don't have to bother going through and checking your border Hessian. If f is convex, and the same things are true on G and H, then you have a minimum. So the Kuhn-Tucker theorem helps you figure out if you have a maximum or a minimum without having to go through the effort of computing border Hessians and stuff. Of course, you're losing some stuff by doing this, right? You have cases in which these conditions don't always hold exactly. These are sufficiently, so what I'm trying to say is these are sufficient conditions. These are enough to get you a maximum, but you might have cases that would give you a maximum otherwise, that you're missing by making these strong assumptions. But I'm guessing that having seen border Hessians in the previous 2 modules, you're not very unhappy about that. Okay, so now we're going to finish off this module by just going through and listing the rules, basically accumulating all we've done so far in this module, and listing the rules for computing optima of a constrained optimization problem with inequality constraints. And note, we're going to assume that f is concave or convex appropriately, and that g and h are quasi-convex at least, so we have an actual minimum, so we have a maximum or a minimum respectively, and don't have to worry about the border Hessians. Okay, so step 1, convert all the constraints to the form gi of x equals 0 and hj of x is less than or equal to 0. Note the most common form of inequality constraint is going to be non-negativity constraints, and these must be written like so. Okay, so that's the first step. The second step is to form your Lagrange type function. I call this, we're going to be f. That's your objective function, the thing you're trying to maximize, really. And then the sum of all your equality constraints, exactly as before, so I. and then your inequality constraints. Okay. This is for a maximum. For a minimum, remember, you change that negative to positive for a minimum. Okay. And again, note, for non-negativity constraint, h equals negative x. So you flip the sign anyway, because you're sticking a negative x in for h over here, for an inequality, for a non-negativity constraint. So step 3 is to get all the conditions. So first we're going to differentiate. We're going to find all the, with respect to all the x's, and with respect to all the lambdas, right? Here we're assuming that there's so to all lambdas as before. Now this might not match the book exactly. I'm just putting them together here. I mean the content matches the book. The number might not. Next, you're going to get your system of Kuhn-Tucker conditions, which involves setting each of the partial derivatives here equal to 0, setting each of these equal to 0, and writing this system of complementary slackness conditions, which will be mu j hj equals 0 for all j. So you do this for all k, which means all the components of x, for all I, so all the equality constraints you have, and all j, so all the inequality constraints you have. These give you your Kuhn-Tucker conditions. Okay. Now, here's the part we give cases. For all cases, we call it case, and there's more detail in the book because you have more room. I have more room in the book than we have on the screen, but we call the cases where for every inequality constraint, either mu is 0 or h is 0. If h is 0, then mu is greater than or equal to 0. If mu is 0, then h is less than 0. So for all cases, do the following. Solve the system of conditions for either, and this is for one condition, but this generalizes, for either mu equals 0 for each j, h is less than 0, or mu is greater than or equal to 0, hj equals 0. So for every combination of cases, you do this. So for instance, if you had two of them, and mu1 and mu2 say, then you would have one case when mu1 and mu2 are both 0, and both h's were less than 0. You'd have one case when both h's were equal to 0, and both mu's were greater than or equal to 0. And you'd have one case in which mu1 was 0, and mu2 was non-negative. And then another case when mu1 was non-negative, and mu2 was 0. So basically every combination of possibilities, remember combinations back in probability, right? Every combination of possibilities creates a different case. So if you have one constraint, you have two cases. If you have two constraints, you have 4, 3, 8, and so on. It's 2 to the number of constraints. So there could be a lot of cases. We're going to stick to no more than 8 pop cases. In the examples I'm going to give here, we're going to stick to actually, I think, 4 cases, just because of screen space. In the book, we can do 8 cases. Okay. So that's step 5. You go through, and for every single case, you solve the system, which produces a critical point x star, a critical point lambda star, and a critical point mu star. So the critical points consist of all the values to all these 3 vectors. Note that you might not get one for every case. And the reason is, unlike in the case of the equality constraints, where you're sort of guaranteed to get something, in the case of the inequality constraints, you're not guaranteed not to violate one of the conditions. And there's 2 ways you can violate conditions. One, you set mu equal to 0. So it's the first situation. Let me put that in red. The first situation, you set mu equal to 0 But you discover when you go through and solve this thing that the solution has h, in that case, be greater than or equal to 0. That violates the assumption on the case, and therefore you don't have any actual critical point there. So you have no critical point, that's x, I guess, no critical point, if h is greater than or equal to 0. In the second case, which I'll write in blue, you have no critical point if mu is less than 0. So if you solve a system and it requires that the mu you find, the mu you solve for is less than 0, that violates the assumption that it's greater than or equal to 0, and therefore you have no actual condition. And therefore you have no actual critical point there because you violate the assumptions on the case. So those are the two ways in which you can go through and remove some of the cases and remove critical points associated with some of the cases. Last step 5, you go through and do this, you solve it, you get whatever number of critical points that still satisfy all these assumptions on the cases and all the other system equation requirements, and that gives you a set of critical points. Then step 6 is the old comparison case. You compare the value of the function at all the possible local maxima and to get the global maximum, and the same thing for the minima, you get the global minima, and you're done. Note again, you just change the sign on the inequality constraints in the ground state function to get minima, so usually you do these problems separately. And since you're assuming different things on F, you're usually doing these things separately, so you're really comparing possible maximum to find the global maximum. You have to do separately to get the global minimum. Okay, so that is it. That's the technique for doing the solving a system. Solving an optimization problem that utilizes inequality constraints. In the next and last module, we will go through and do a couple of examples. Thank you very much.